Okay, so this lesson, 37-2, is exactly the same as the last lesson. It says that we are describing how changing the dimensions affects the perimeter, area, surface area, and volume. The slight difference is last lesson, they gave us how the dimensions were changed. They said the dimensions are being tripled, or they said the dimensions are half. They gave us the dimension change. That dimension change that they were giving us, that's called the scale factor. In this lesson, we're going to have to determine the scale factor. And you've already done this because you've already done similar shapes in previous lessons. So I'm just going to remind you, there's a couple of things that you have to remember when you're trying to figure out how the dimensions changed. You have to compare corresponding parts from the triangles. So for example, they said which of these triangles are similar. To determine that, we're going to compare the height of this triangle to the height of this triangle. And it is also important to indicate which one is considered the original one versus which one is the new one. Now, not so much like you can get the scale factor either way, but you do need to know which one you started with versus which one you're going to. So for example, pyramid 1, I'm assuming that's my original one. So I would put those measurements. Let's do the heights first. I'm going to put the height of that one on bottom, and I'm going to compare that to the height of the new one. And then of course I'm going to reduce it down to its most reduced form. And 10 over 12 reduces down to 5 over 6. We canceled out a common factor of 2, I believe. So this reduces down to 5 over 6. Now we have to check a second dimension. Checking one dimension alone is not enough. We have to check a second dimension, and it should also reduce down to 5 over 6. If it doesn't reduce down to 5 over 6, then they're not similar. So we're going to compare a different measurement. We're going to compare the base edge to this base edge. We have to be sure and consider pyramid 1 is the original one, so it goes on bottom. And then 17.5 is going to go on top. And now we see if that reduces down to 5 over 6. Again, I'm using a calculator. I'm typing 17.5 divided by 20. And when I do that, I get 7 over 8. That reduces to 7 over 8. Since 7 over 8 is not equal to 5 over 6, pyramid 1 is not similar to pyramid 2. So I'm trying the next two triangles. I compare, I assume pyramid 1 is pyramid 2 is the original one. So I am comparing the heights. So I take 10, I put that on bottom. I take the 8. Corresponding parts need to be written as a ratio with the original on bottom, the new one on top. And then it reduces down to 4/5. So that means the scale factor of this one for the heights is 4/5. I also need to check to make sure that the edge length has the same scale factor, because any dimension from this triangle should be any dimension from the pyramid 3 should be 4/5 of pyramid 2. So that one is, we have to check these dimensions down here, and I didn't put a box around this one. So I put 14 on top, 17/15 on bottom. I'm going to use my calculator. I finally turned my online calculator on. So I'm going to type in 14. Actually, I'm going to put a fraction bar and put 14 on top and 17.5 on bottom. My calculator is set to give fractional answers, but I'm expecting it to maybe not, because the calculator does not like decimals in a fraction. That's what I thought. So because I have a fraction that contains a decimal, it automatically changed it to a decimal. Now we do have a feature that will allow me to change that. Now I could just say, I'm wanting to see if this reduces to 4/5. So I could just type in 4/5 and see if it gives me the same decimal. And of course it stayed a fraction, but I can put that right there and do Control Enter, and it'll change it to a decimal. So I see that 4/5 is 0.8, but I can also go back and grab this number right here and click the menu button, click number, and it will approximate it as a fraction. So I want to have it change it to a fraction, and it changes 14 over 17.5 to 4/5. So it does reduce. So that reduces down to 4/5. I got the same scale factor for both measurements. So that means that pyramid 2 to pyramid 3 has a scale factor of 4/5. That is my scale factor. Now that is going to be important because the scale factor is the same thing that we did a while ago when we were determining the change in the dimensions. So we're going to use that 4/5 to find the a missing area or a missing volume. So in problem 2, Howie has built a square pyramid. The base edge is 10 and the height is 12. He knows he needs the height of the second pyramid to be 24 centimeters. Determine the scale factor. So what happened to our dimensions? The ones that we know for both pyramids, we know the height is 12 and we know this height is 24. That should be pretty easy to see that what do we have to do to the 12 to make it become a 24? We have to multiply it by 2. So the dimension change for the height was times 2. That means all dimension changes are going to be times 2. But when they ask you for the scale factor, remember the scale factor is always written as a ratio, and we always want to put the bottom or the original number on bottom, and this says determine the scale factor of the small pyramid. That means they're calling this one the original one, that's the one we're starting with, to that of the larger one. We know that the answer should come out to be 2, and we should be able to see that it's 2 because we put the known measurement from the first one, which was 12, on top, the known measurement from the second one on bottom, and then we reduce it. So the scale factor is said to be 2 or 2 to 1, and they are also often written like this. The scale factor is 2:1. That means we say 2 to 1. Same thing with a fraction. The scale factor, the change in the dimensions was times 2. Just write the times 2 as a fraction. How do you write 2 as a fraction? Put it over 1. But these should all be the same kind of thing. Now determine the length of the base edge. So we're talking another dimension. So the base edge has to double. So if it started off being 10, 10 times 2, the base edge is going to be of the other pyramid is going to be 20. So on problem number 4, I filled in all the information. I know on the previous page we wrote the ratio as pyramid 2 on top and pyramid 1 on bottom. They specifically told me to do pyramid 1 on top, pyramid 2 on bottom. So I did what they said. On the previous page, we got the ratio to be 2 to 1. This time the ratio by the way they defined it is 1 to 2. It pretty much says the same thing. If we say the ratio is 1 to 2 compared to 2 to 1, it pretty much says the same thing. It's saying that the bigger one is going to be double the smaller one. And this way right here is implying that we started with the smaller one and then we doubled it to get the bigger one. This is saying we started with the bigger one and we halved it to get the smaller one. Again, it's the same ratio. You've got a big one and a small one, and the big one is twice as big as the small one, or the small one is half as big as the big one. It's saying the same information. So notice that everywhere we have an inch, the dimension is just in singular inches. The ratio was 1 to 2, 1 to 2, 1 to 2, 1 to 2. As soon as we started finding measurements that had a square inch, and it says square inches right there, the ratio is now 1 to 4, 1 to 4, 1 to 4, which is the scale factor. All of these right here are the scale factor. The scale factor is equal to 1 to 2. All of these right here, where the ratio was inches squared, we took the scale factor and we squared it. And then the one where we have cubic inches, we took the scale factor, which was 1/2, and we cubed it, and we got 1/8. So that is the relationship that you need to be aware of for all solids. Doesn't matter whether it's a pyramid, a cylinder, a sphere, a cube, a prism. That relationship that we just discovered right there is the true for all of them.